we'll be doing a titration in the lab during Chapter 15. We titrated earlier in the year, but this is even going to be easier. We're going to let the computer do all the work for us. We're going to start with an acid. In this case, we have 100 milliliters of 1 molar hydrochloric acid. We'll add an indicator, and then we'll add a pH probe. And as we titrate or add the base to the acid, we're going to let the probe measure the change in pH as we add sodium hydroxide. You don't have to do a darn thing. It's great. Eventually, we'll get a graph that looks like this, and there are a few things that we'll want to get off the graph. Number one, this is the titration of hydrochloric acid and sodium hydroxide. Strong acid, strong base. So I would want to choose an appropriate indicator. I need an indicator that's going to change colors somewhere around a pH of 7. That's when I should hit the equivalence point. The one they're using here is bromothiamyl blue. We'll call it BTB. That bromothiamyl blue should start off yellow in the acid, and then it turns blue when it's basic. At the equivalence point, when it's neutral, since this is strong acid, strong base, we should see green. Obviously, on your black and white lecture guide, you can't really see that. We can mark those colors in, and often on an indicator chart, they'll list those colors. Now, if I were doing a titration without the computer, we would mix the acid and base, and we try to stop at green. The equivalence point is when I have equal moles of acid and base, hydrogen, hydroxide, according to the ratio in the balanced equation, which again, if it's strong acid, strong base, the pH should be neutral. So we try to stop the titration when it's green. If you graph it, this is going to start off pretty low, maybe a pH of 0, I don't know, it depends on the acid that we're using. As we add the base, obviously the pH should go up. And all of a sudden, you'll just see this giant gap in pHs where we shoot up, and it might be like one drop. One drop changes the pH like 4, 5, 6 units. And then all of a sudden, it kind of levels off again. Somewhere in that one drop, you hit the equivalence point. You've probably titrated like in first year chem, and sometimes it's hard to stop the titration at the perfect equivalence point, because one drop has like billions and billions of ions. Somewhere in that one drop, you hit the equivalence point, and you probably had even more than the equivalence point. So if we titrate using the computer, we can go beyond the equivalence point. We can graph this thing for the entire burette of in this case, sodium hydroxide. When you see that giant gap in pH, go right smack in the middle. That's your equivalence point. And on the graph, it's a little bit of an estimate. So maybe this is kind of right in the middle. If you follow it across, you'll get the pH at your equivalence point. If you follow it down, you get the amount of base added at the equivalence point. Which again, like often we try to stop the titration when we hit the equivalence point, and then we measure on our burette, how much base did we add? Well, this time we're just going to let the whole burette empty. How much base was added at the equivalence point? We can find that on our graph. Take that midpoint, follow it down. Now this graph is moles of sodium hydroxide. When we do this in the lab, it'll be volume of sodium hydroxide. And then if we know the molarity, we can figure out how many moles were added. Let's just see if this makes sense. So according to the graph, the equivalence point is at about 0.1 moles of sodium hydroxide added. Well, look at this. We have 1 molar acid, which is moles per liter, 0.1 liters. Perfect. That really would be 0.1 moles of acid. And that matches the amount of base at the equivalence point. So here's a real typical graph of a titration of a strong acid, strong base. Now obviously we can switch that, and our graph might look a little bit different. So here's the titration of a weak acid and a strong base. So one of the things I noticed right away, the equivalence point. Look at the pH. If you go halfway in the middle of that big jump, and again, that's kind of an estimate, and then we follow it across, our pH is still slightly basic, which is exactly what I would expect, even though we're at the stoichiometric equivalence point. Because again, if I follow this down, I've added 0.1 moles of sodium hydroxide, and this would be 0.1 moles of acid, but it's a weak acid. I'm at the stoichiometric ratio in the balanced equation, but because of the nature of the particles, it's not neutral. The sodium hydroxide dissociates 100%, so I get a lot of hydroxide in the solution, but the acetic acid will not dissociate 100%. So most of that 0.1 moles of acetic acid, that stays neutral molecules. I do not produce enough hydrogen to match up with 0.1 moles of hydroxide. So again, even though we're at the stoichiometric ratio in the balanced equation, we're at the equivalence point. Because it's a stronger base that dissociates completely, my pH will be slightly basic. Other things that I don't catch my eye, we've used a different indicator. This time I want an indicator that'll change colors slightly basic. The one used here is phenolphthalein. Which is real common. You probably use this one in first year chem. It starts out clear in the acid, and at the equivalence point, you try to stop at like the first signs of pale pink, like cotton candy pink. If you go one drop too far, it turns like 80s hot pink. It gets like super bright pink. It's a beautiful color, but you've gone beyond your equivalence point, which is why we usually titrate more than one trial. Unless we're going to let the computer do it for us. Because again, we're just going to go beyond the equivalence point and get this entire graph. So we'll let it start acidic, we'll go through the equivalence point, we'll let it end basic. From the graph, we'll get the pH at the equivalence point, and we can follow it down to figure out how much base was added at the equivalence point. This is a real tough one to do in the lab. You might remember this one. If you seriously go like half a drop too far, it turns hot pink right away. But this is a typical graph. The shape of the graph is representative of the titration of a weak acid and a stronger base. So what if we wanted to sketch the titration curve for a strong acid and a weak base? So they're giving me this generic graph. I'm assuming it's maybe pH versus, I want to guess volume. Let's say volume of weak base. Added. When we do this in the lab, it's going to be volume. So I'm assuming maybe that's like 5, 10, 15, 20 milliliters. That's kind of what our data is going to look like. Okay, so let's say I start with a strong acid and I mix it with a weak base. They're not really telling me the volume added at the equivalence point, so I'm just going to make something up. But I know that my pH at the equivalence point should be slightly acidic. So I don't know, let's say I start out pH close to 0, a strong acid, it's probably pretty acidic. And then it's going to go up slightly as I add the base. And then I'm going to get that jump, and then it should kind of level off again. Oh, that's pretty cute. That might be one of my best. So I just randomly chose 20 milliliters just because it's kind of right in the middle. But the other thing that would be important about this graph would be if I go like halfway in the middle and follow it across, my pH should still be something slightly acidic. The strong acid dissociates completely, but the weak base does not. So even though I have equal moles according to the ratio in the balanced equation, that weak base will not produce enough hydroxide to match up with the hydrogen coming from the strong acid. You could flip these. We should make note that these examples were all like starting with the acid and adding the base. The pH went up every time. You could do the opposite. So you could have something that looks like pH, and then let's say this is like volume of acid added. So if you started with the base and added the acid, the graph is just kind of flipped. The pH would start up high, and then you'd have a big jump in pH units, and then it would level off again. And so again, somewhere in the middle of this gap, I could follow it across and get the pH at the equivalence point. I could follow it down to get the volume of acid added at the equivalence point. So we should just make note that you can start with the base and add the acid. The other thing they're asking me here, they want to suggest an appropriate indicator for this titration. So again, often on the AP test, they're going to give you a list of possible indicators. We had a list earlier in the study guide, and I would only want to choose then the indicator that's appropriate for that titration, which they're only going to give you one good choice. So randomly, my pH was maybe like 4-ish at the equivalence point. So I might want to choose something like methyl orange, where it should change colors somewhere around a pH of 4. Or if they gave me Ka values, if I did opposite log of the Ka, the color is going to change at about 4. Or again, sometimes they might give you just pKa's, which is the opposite log of the Ka. We want an indicator that will change colors when the pH equals the opposite log of the Ka value. So with this one, maybe methyl orange would be the best choice. And again, they're not going to give you something where there's more than one good choice of indicator. So an appropriate indicator, maybe methyl orange. Perfect. So qualitatively, those are maybe the most important things I'm looking for off a pH graph, a titration curve. Another type of titration curve that we should mention is for a polyprotic acid. Remember that we kind of mentioned polyprotic acids don't just spew all their hydrogen at once. It's kind of a step-by-step process. The hydrogens come off one at a time, and there's usually separate K values. You'll see that on the titration curve. There'll be more than one equivalence point. If this is sulfuric acid and sodium hydroxide, sulfuric is a diprotic acid, it might look something like this. So somewhere in here, we'll call this like the first big jump. That's my first equivalence point. That would be the first dissociation. So that would be the H2SO4 splitting into the hydrogen sulfate ion. And the first hydrogen. Excellent. The second equivalence point, which is listed here as point A, is for the second dissociation. This would be the hydrogen sulfate ion, SO4 minus, releasing that second hydrogen. So forming the sulfate ion. And there's the other hydrogen. So just make note, you're not going to have to do any crazy calculations with titrations involving diprotic or polyprotic acids. But qualitatively, they might ask, like, what kind of a titration is this graph? This is a diprotic acid because there's 2 equivalence points. Or they might ask something like this. What is the identity of the an ion at point A? The an ion is like the negative ion. And so at point A, my second equivalence point, that's when I finally form the sulfate ion. This bad boy. There's my an ion from the second dissociation. Perfect. You know everything there is to know about titration curves, and we will get these beautiful graphs in the lab.